Okay, we're going to start chapter 5 now. This is what Schroeder calls free energy and chemical thermodynamics. I prefer to call it free energy and applications of thermodynamics because we'll be looking at things that aren't strictly chemistry, at least in my opinion. Um, Most importantly, I'd like to motivate why we want to do this, because when this material was first introduced to me as a student, I was sort of overwhelmed by this alphabet soup of H, F, G, P, V, S, T, and I was being asked to calculate all these derivatives, and it would be good to know why this is worth doing. And so I'm just going to start with a few examples, and it's not my intention that you understand in detail any of these, but just to show you that this is going to be a worthwhile exercise. So the first is the phase diagram of water. Good old H2O. This is the PV plane showing the three phases that we know as ice, liquid water, and steam. Of course, we normally live at 1 atmosphere, so as expected, ice melts at 0 degrees Celsius and vaporizes at 100 degrees Celsius. That's this point here. Now, trying to calculate this phase diagram from first principles would be an impossible task, and it's not going to be our goal. What we would like to do is to understand some basic properties. For example, there's a point here known as the critical point at which the latent heat of vaporization vanishes. Another important fact about the ice-water phase diagram is that if you look at the slope of this boundary between solid and liquid, it actually tilts in this direction, meaning that as the pressure increases, actually the melting point decreases. That's a little bit strange, and it's not something we could actually calculate from first principles. But as we'll see in this chapter, we can relate it to another common fact about ice and water, which is that ice is less dense than water. Right? So those are just a couple points about the water phase diagram. Another example of great interest to physicists is superconductivity. So this is a phase of matter in which there is zero electrical resistance. So this happens at low temperatures for lead below about 5 degrees Kelvin. So in this case, what's interesting is that there is a phase diagram with respect to magnetic field and temperature. And at low temperatures and low magnetic fields, metals like lead, mercury, aluminum have this miraculous property of having zero electrical resistivity. Outside of this region, their behavior is what we call normal, meaning that of a normal metal. Right? In this case, as an example, it was not until around 1955 or so that we understood the microscopic origins of this phenomenon. But using thermodynamics, long before that point, people basically understood the behavior shown here. For example, the relationship between this so-called critical magnetic field and critical temperature. So here's another example, which is the phase diagrams of binary alloys. And these are a classic case of applications of thermodynamics. So shown on the left is copper nickel. This is what's known as a solid solution. Copper and nickel are right next to each other in the periodic table, and they crystallize in the same structure. So among other things, this means that they're soluble in both the liquid form, which may not be that surprising. So if you melt them together, they mix. Right? But also in solid form. So they form a single lattice, and you might find copper or nickel on each side. So the phase diagram is temperature on one axis, percent nickel concentration on the other axis, and they're really just three regions. At high temperature, the liquid, below the melting point, which depends on the concentration of nickel. There's this single solid. There's this coexistence region in the middle, which is coexistence of liquid and solid, which I'm not going to discuss now in any detail. Now, most binary alloys are much more complicated than this. So classic case is that of lead and tin. So this is what make up ordinary electrical solder. And these do not form a simple mixture in the solid phase. So in this case, we have temperature on this axis. This might be percentage of tin in lead. On the x-axis, you see multiple phases in this diagram, which I'm not going to attempt to explain at the moment. One curious feature, which is of great practical utility, is that the melting point of this so-called eutectic discomposition, which is about 60-40 of lead tin, is a minimum. Right? And this is a good thing if you want to work with solder at a low temperature. And in the solid phase, what you get is, instead of a homogeneous mixture like we did for copper and nickel, two phases, alpha and beta, which coexist, and they form this sort of granular microstructure. So this inset here is actually from an electron micrograph. And this structure is what gives the solder its strength. Lead and tin are both soft metals, but in fact the alloy can be much stronger than either of them by themselves, and that's a property of this mixture. So we would like to, if possible, be able to understand something like this phase diagram. Now it gets even more complicated than that. I'm showing in the lower right here the phase diagram for brass, which is an alloy of copper and zinc. The brass that you're familiar with is about 30% zinc and copper. So here you see this multitude of different phases, which I don't understand myself. At high temperature, again, there is a single liquid phase. At low temperature, this multitude of different solid phases. Okay, so let's take an example from magnetism. So this moves us a little bit closer to the main point of this chapter. So in the case of the paramagnet, which we've seen before, we defined the magnetization as essentially the difference between the number of up and down magnetic moments. And for a material like iron, it will be magnetic, meaning this difference n up minus n down will be non-zero below some critical temperature, which is about 1,000 Kelvin. Right? So at higher temperature, n up and n down are the same. This isn't surprising if we were considering only entropy, which is maximized when n up is equal to n down. But below that temperature, the tendency of the magnetic moments in iron to want to be parallel to each other causes this to be non-zero. So that's why at low temperatures, iron is actually magnetic. So it's sort of overcoming the tendency of entropy to make it disordered. So the question I would like to ask is whether there's some analog to potential energy in this problem. And I put this in quotes because it's not like a potential energy at all, but some sort of energy that we could use in a manner similar to that in which we use potential energy in classical mechanics. So if you remember in mechanics, equilibrium occurs when the potential energy is a minimum, so at the bottom of some sort of parabolic curve, right? That would correspond to mechanical equilibrium. In this case, is there a way to consider thermodynamic equilibrium in a similar context? So for example, if this curve, which at the moment is completely hypothetical, of energy, which is a function of, let's say, magnetization and temperature, had only one minimum, as for the blue curve here, which occurs at magnetization equals 0, this would describe iron at high temperatures. So this function is a minimum when m is equal to 0. On the other hand, one might have a curve that is like the orange one, right, which has minima which occur at non-zero values of the magnetization. There are two of them. They would correspond to the magnetization pointing north or south. Right? And below the critical temperature, this hypothetical curve might look like this, And if we minimize this function in this regime, the minima occurs at some non-zero value of the magnetization, or some non-zero value of n up minus n down. Right? So my point here is that if we could possibly construct such an energy, and I don't know how to do it yet, right? And could figure out how to use it and exploit it, we could understand systems like magnetism, and for that matter, the examples that were on the previous view graphs. Right? The problem is that it's not exactly clear how to do that. There are many ways to construct an energy, particularly in thermodynamics. And the other thing that is complicating is that the choice of such an energy will vary depending on the experimental conditions. For example, are we working at constant temperature and volume, as we did in Chapter 6, or constant pressure and temperature, as we do in real life in the lab? Right? And depending on which of those conditions prevails, one would pick a different type of energy. But that's our general program, is can we find this analog to potential energy in mechanics that we can use to understand thermodynamic systems. Okay, so as I just said, this is sort of the program. We want to apply what we've learned so far this semester to more complicated problems like phase diagrams, coexistence of phases, for that matter, chemical reactions. Right? As in classical mechanics, we would like to use the language of energy to do so. Now, I want to point out that this is not simply an academic exercise, and I'll draw from, again, from last year. When energy was introduced, chances are it was done so through the introduction of work, right? Which is a real thing that we can measure because we can measure forces and displacements. That was related to kinetic energy. And then potential energy was a defined quantity. It's sort of a theoretical concept. Right? U is minus line integral of F dot dr. And here, by the way, U I am using for the good old-fashioned mechanical potential energy, not internal energy. And then you showed that you could do useful things with this potential energy. You could discuss energy conservation. This quantity E equals K plus U is conserved. You'd analyze problems like the Kepler problem in celestial mechanics. We could relate the derivatives of this potential to useful things. So, for example, the fact that U is minimized in equilibrium is equivalent to stating that the forces vanish in equilibrium. So that's F is minus du dx is equal to 0. For that matter, you could calculate things like the frequencies of a harmonic oscillator from second derivatives of U. Right? So my point here is that this potential energy was made up. It was a concept invented by physicists, and it has survived both in textbooks and as a useful everyday thing because it's useful. Right? It provides physical insight, and it's useful for calculations and understanding systems. Right? And we're going to be extending this concept now because we're going to be defining other types of energy. And at first it might appear that those are sort of arbitrary definitions, but the ones that survive, and I'm only going to be introducing those that have survived, are definitions that have proven to be useful over time. Right? And so that's the program. We want to define forms of energy that are useful for interpreting experiments and doing calculations. Okay, so can we do something similar for thermodynamics? Follow this program. And what I would like to do for start is to make up a wish list for the types of energy I want to define. Right? This is still in quotes. There are going to be several different forms of energy that we're going to use. Right? But for these to make the cut and survive to be in Schroeder's book, they've satisfied at least a couple of the items on this so-called wish list that I've made up. So the first is that if something is going to be useful to us, it should have a simple and useful physical interpretation. Right? So certainly a mechanical potential energy has a physical interpretation, right? And that's something we're going to want to see out of essentially any of the quantities we define. If possible, we would like to relate the energy we define to quantities which we can measure easily in the laboratory. We saw an example earlier this semester in enthalpy, which I'm going to talk about again today. Right? Enthalpy was easily related to heating, right? And that's one of the reasons that it's useful. So the third is really a central point of this chapter, which is we would like to relate thermodynamic equilibrium to a minimum of an energy, just like mechanical equilibrium corresponds to a minimum of the mechanical potential energy. And I mentioned last week when I introduced the Helmholtz free energy that it's minimized in equilibrium at constant temperature and volume. I'll show this today, right? This is in that example of magnetism, it was exactly what I was talking about. You know, some sort of function which we can minimize in equilibrium and use that to talk about our system. Then finally, the fourth item on this list, once we have this energy, we would like to be able to calculate other things from it, just like we could calculate forces from derivatives of the mechanical potential energy. We would like to calculate various quantities from derivatives of our thermodynamic energy. So in moving forward from here, I should point out we'll settle for some of the things on this list. It would be nice to get all four at once. The so-called Gibbs free energy comes close to doing this, right? But we'll settle for some of them. It's not a trivial exercise. There are a lot of ways that we could define these energies. Only some of them are useful, and they're going to be dictated by experimental constraints. So for example, as I've mentioned before, whether at temperature, constant temperature and volume, constant temperature and pressure would dictate whether we use one form or another. So there's not a single answer here. The reason why 4 or 5 different expressions for energy appear in this chapter is that they describe different experimental situations. Okay, so there are multiple candidates for energies of interest in thermodynamics. And to start, let's just consider the various quantities we've dealt with this semester that even have dimensions of energy. So the first is the internal energy itself. Right? This is something that does have an obvious physical interpretation and is naturally going to be in our list. The second is work. So pressure times volume is certainly related to work. If the pressure is constant, then P delta V is just the work done. So PV is something that would be a candidate to appear in a form of energy that's useful. Next up is heat, right? So TS or T delta S for a process that's occurring at constant temperature. I'll assume for the moment that we're talking about reversible processes. But TS is a term that would appear in a thermodynamic energy. And then finally, although it's going to have a somewhat lower profile because for pretty much most of this chapter, we're going to keep the number of particles fixed. We can vary the number of particles in a system, and that means there's this chemical potential energy mu times n. Right? So in principle, I could try to define a new form of energy by taking any combination of these 4 quantities. Right? Of course, there's an infinite number of ways to do that if I include numerical prefactors. And as you might suspect, most of them are neither physically insightful nor useful in any way. And we're all going to focus on the ones that are. Right? There are 5 really that are of general use, and 4 which we're going to talk about in this course. We won't really talk about the grand potential. But in order, they are the internal energy, which we've already seen. Enthalpy, which we saw in chapter 1. This is U plus PV. The Helmholtz free energy, which I introduced last week with a promise to discuss it in more detail, which is what I'm going to do today. That's U minus TS. And the Gibbs free energy, which is U minus TS plus PV. So I'm going to show now that these satisfy at least some of the items on our wish list and are worth keeping around. But absent the first of these, the second, third, and fourth are just definitions, right? And they've survived because they're useful definitions. I'm not going to talk about the grand potential today at all, right? But that is the Helmholtz free energy minus this mu times n. And it becomes useful in problems where we're letting the particle number vary. All right. So let's start with the internal energy. And before doing that, there are some things to just keep in mind throughout this. And this slide is supposed to emphasize those things which I really expect you to remember, because with so many definitions kicking around, it's easy to get frustrated. But if you remember a few things, you can always sort of reconstruct thermodynamics. So the first thing is, first law of thermodynamics, always true. Delta U is heating plus work, right? The second principle, which was a big point in chapter 3 of Schroeder, is we can think of equilibrium as a state of maximum entropy. So things will tend to evolve towards maximum entropy. This is a statement of the second law. And the universe, as I use it in quotes, corresponds to a reservoir, a large entity that contains our thermodynamic system. So we already dealt with this in chapter 6, right? And the entropy of the universe, which is essentially the reservoir and system together, evolves towards a maximum, right? Now, that's a truism. Unfortunately, it's not very useful because we can't control or measure entropy directly, right? So that's one of the things that motivates the need for some other quantities to either minimize or maximize an equilibrium. The third thing to keep in mind here is the thermodynamic identity, right? So this we need to remember, right? du is TdS minus PdV plus mu dN. And these were all originally defined in chapter 3 from this entropic maximization principle, right? So it turns out that if you memorize the definitions I gave on the previous view graph and you know the things on this view graph, you can rederive everything else in chapter 5. So it's not a matter of just memorizing endless derivatives and things like that. We can, in fact, rederive all those things. But I will be appealing to things on this view graph again and again. Okay, so now let's look at, okay, so for the internal energy U, the first item on our wish list, it's pretty clear. It does have a obvious physical interpretation. There are some points of judgment, like what we choose to include in the internal energy. In the case of the ideal gas, it was the kinetic energy, the rotational energy of the molecules, their vibrational energy. We didn't include mc squared, the rest energy of the atom. So one always has a choice as to what they include in U, but it has an obvious physical interpretation. It's perhaps not as useful as we would like, as we'll see. It's not a minimum at thermodynamic equilibrium under general cases. So it's not going to satisfy item 3 on our list. We can relate it to some measurable quantities, such as the heat capacity. Heat capacity constant volume is du dt, right? And moving down to item 4 on our list, it is easy to calculate. We saw that last week in the case of the canonical ensemble, where the temperature and the volume were fixed. We could calculate the partition function, and we could calculate the internal energy of the system. I guess I'd have to multiply the number of particles, but there was a well-defined recipe for calculating the energy. And also, we can calculate other things from U because we have the thermodynamic identity. So, for example, T would be du ds if we keep V and N fixed, etc. Right? So, the internal energy is certainly a useful thing. It's not, as I pointed out, a minimum. It's sort of what would be called thermodynamic equilibrium at any non-zero temperature. It's just not useful for that. So that's one of the things that motivates looking at other things. It's also relatively difficult to measure directly. We can get it sort of indirectly from heat capacity, constant volume, but that's also sort of a difficult thing to measure. So it's perhaps not as useful as we would like it to be, but it's a good thing nonetheless. All right. So down our list, the next thing was a friend because we've seen it before, and that's the enthalpy. H is U plus PV. Right. So let's go through our wish list of items. First is there a clear physical interpretation? And the answer is yes. As we discussed back in chapter 1, this quantity H represents the internal energy of the system plus the work done on the environment to create it. So if we're at atmospheric pressure and I create some system that occupies a certain volume V, I've done a amount of work, PV, on the atmosphere, right, in the course of creating the system. And if I'm bookkeeping the total amount of energy, I should include that, not just the internal energy of the system, but the additional work that I did to create it. Right. So, by the way, just to recall, we're talking about work done on the environment. Right. All right. So that's the physical interpretation. Is it useful? And as we found in chapter 1, the answer is definitely yes. Let's go back to the first law. We wrote delta U is Q plus W. As we just said, at constant pressure, P delta V, which is the work done on the environment. Delta H is this. We can use the first law in this expression, where now W is the work done on the system. That's minus P delta V. That cancels the P delta V here, right? Where I'm including this W other. So this is the work done that's non-compressive work on our system, right, which I should also include in the first law. And when we're done, the compressive work done on the system, which is this minus P delta V, cancels the P delta V on the environment. So delta H is just the heating Q plus other forms of work. And in many experimental situations, this term can be 0, in which case the enthalpy change is just equal to the heating, right? And this is very useful because heating is something we can measure. I can measure how much heat I've applied with my Bunsen burner, right? And therefore, we can keep track of this delta H during all sorts of types of reactions, particularly those that occur that are isobaric at constant pressure. That's why it's in tables, right? So we can keep track of delta H, tabulate it. It's a useful thing. Okay, so that takes care of the first couple items on our wish list. Now, third and the fourth are not something we dealt with in chapter 1, right? And for this, it's helpful to look at dH. So let's look at the differential of this enthalpy. And because H is U plus PV, I'm going to use du, which I'll get from the thermodynamic identity. And now there's an important trick. We're going to go d of PV, which is PdV plus VdP. All right. I'm going to mention this again towards the end of the lecture. This is what's called a Legendre transformation. And if I write out the thermodynamic identity, TdS minus PdV plus VdN, our expression for dH is TdS plus VdP plus mu dN. Right? So I do have a bunch of things I can calculate from H, these three derivatives. But if we recall point 3 on my list, which was, can we minimize H in equilibrium? We're sort of faced with this awkward problem, same one we had for internal energy, that S appears here, right? And S is not something that we can easily measure or control directly. So this limits the application of enthalpy, right? So items 3 and 4 on our list, not so good. These derivatives do exist, but as I said, we're sort of limited by this awkwardness of S appearing here. Right. Little side note here, this differential dH, once you get the hang of it, you can always rederive it, because if you If you memorize the definition of H and you memorize the thermodynamic identity, you could rederive everything I did on this view graph. So keep that in mind. All right. So to sum up here, enthalpy, it's a useful quantity. Doesn't satisfy everything on our list, but it's certainly good for certain things like keeping track of heats of reaction. So let's move on. And now we're going to talk about the Helmholtz free energy, which we introduced last week. So some of this I'm repeating from then. Right? So first of all, does it have a physical interpretation? Right? And it does. In this case, we're starting out with internal energy and we're subtracting off essentially the heat that is stored in the system. That's objectionable language to some people. But if somehow I were to make my system completely disappear under constant temperature definitions, this S would have to be transferred to the environment. Second law requires that. Maybe even more entropy would have to be created, but at least this much heating would have to be given up, which tells me that if I want to extract work from my system, I would have to, as a starting point, take this amount of heating and subtract it from U. Right? So the Helmholtz free energy tells us essentially the maximum amount of work that is available in our system. Right? And that's the origin of the name, the amount of energy that's free to perform work. Once again, we can stick this into the first law. All right, delta F is basically delta U minus Q, that's work. So the change in free energy is the work of any type done on the system if the process is reversible. Schroeder is a little bit more careful. He covers the irreversible case, in which case Q, the amount of heating, is less than or equal to T delta S, and delta F is less than or equal to the total amount of work. Right? So as I said in point A, Helmholtz free energy tells us essentially the maximum amount of energy that's available to perform work. Right? So there's a clear physical interpretation of the Helmholtz free energy. I will point out here that W here refers to any type of work done on the system. Okay, now in principle, if we had an easy way to keep track of work, right, we could calculate F and tabulate it just like we can tabulate enthalpy by keeping track of heat. Unfortunately, work, when you got pressures and volumes changing, is not an easy thing to calculate. So you will not find tables of Helmholtz free energies around. You could actually make those tables from calculations, but it's not the type of thing that can be based on easily on experimentally measured quantities. So point 2 here, it's a little bit weaker perhaps than for enthalpy. But this is more than made up for by the advantages of the Helmholtz free energy with respect to points 3 and 4 on our wish list. And so let's see why. Right. So this is a point I made last week, and the proof is in the text on page 161, which is basically what I'm replicating here. Right. So we're going to assume that n is fixed, and I'm just going to say we're going to try and minimize f at constant t and v. And I'm going to show that this is basically identical to maximizing s for the combination of the system and reservoir. So the entropy of our universe, and remember our universe consists of reservoir plus system. The entropy of our universe is S total, so that's S sub r plus S. So there's no subscript for the system here. So if I just write S, that means entropy of the system. Right? As a calculus problem, we would want to set ds equal to 0 in equilibrium, and that's going to correspond to a maximum of the total entropy. So that's what we learned from chapter 3. And besides that, really all we need to remember is that energy conservation still applies. So if I have exchange of energy between system and reservoir, if the energy of the reservoir increases by du, then du sub r, then the energy of the system has to decrease by minus du because their total has to be 0. Okay, so V and T are fixed. This makes our thermodynamic identity very easy because two terms are 0. It's just du sub r is now T dsr. And we can write an expression for TDS total, taking S total from here, as TDSR, but that's just DUR from here, plus TDS, right? DUR is minus DU, and this quantity here is just minus DF, right? So this is just math, right? But it has very important consequences because now we see that really DS total, the entropy of the universe, meaning system plus reservoir, is proportional to minus DF. And therefore, if we're maximizing S total, we are minimizing F, F being the free energy of just the system, right? And so this is why the Helmholtz free energy is a big deal. At constant volume and temperature, maximizing entropy of the system plus reservoir, which is what we do in equilibrium, is equivalent to minimizing the Helmholtz free energy. So we have a quantity here, this F equals U minus TS, which is a minimum in equilibrium at constant temperature and volume. All right, so let's just see how this plays out. One quick example. This is qualitative. I'm not going to do any calculations here, but we've already done the paramagnet. Right? We did it actually twice so far in the class. Right? Here's the Helmholtz free energy, U minus TS. And just recall that we like to talk about the magnetization of the paramagnet, which is, once again, the difference of the number of up and down spins. And what do we need to do to minimize F? And how is that related to the magnetization? Okay. Well, obviously, if it was just a matter of minimizing U, that's just a matter of making all moments parallel to B, because minus M dot B is the internal energy of the system. Similarly, if it's just a matter of maximizing S, and note the minus sign here. So at high temperatures, we have this factor of T here. Minimizing F is always just going to be a matter of maximizing S. And that's a maximum when N up and N down are equal. That maximizes the multiplicity of the system. So at low temperature, where this term in the free energy, the minus TS, is 0, then minimizing F is just a matter of minimizing U. That's sort of intuitive. And that's why at T equals 0, the energy minus 1 in the units I've plotted here just means all the moments are parallel to B, and the magnetization over here is a maximum. At high temperatures, this term, minus TS, wins in our effort to minimize F. Right? We want to maximize the entropy. Entropy approaches its maximum, which is basically NK log 2. Log 2 is 0.69. Right? And the magnetization goes to 0 because to maximize S, we're letting N up is equal to N down. Right? So that's just sort of a qualitative example of how, in practice, F does get minimized. We could calculate these quantities from the partition function, which we did it last week. Here's F. Okay, so item 4. Can we calculate other things from F? So we're going to do what's similar to what I did with enthalpy. Start from the definition of F, take its differential, substitute for du using the thermodynamic identity, TdS minus PdV plus UdN. Right? The differential of Ts is TdS plus SdT. So we're done with this. We get this expression for dF, minus SdT minus PdV plus mu dN. Right? So this may look like, once again, just a series of manipulations, but now actually the result's fantastic because we have a way to calculate the entropy easily, right? Because I've shifted the independent variable from S to T. S is just minus dF dt, keeping V and N fixed. P is minus dF dV, keeping T and N fixed, and chemical potential is dF dN, keeping T and V fixed, right? So to sort of complete the picture, as we saw last week, we can calculate F from the partition function. It's minus kBt log z. And we can calculate all these other quantities from derivatives of F. Right? So Helmholtz free energy is a pretty good thing. It clearly satisfies 3 of the 4 things on our wish list. It has a clear physical interpretation. It's calculable. It's minimized under a specific set of laboratory conditions. And we can calculate other things from it. It is a little bit difficult to sort of keep track of directly in the laboratory because work is a hard quantity to measure directly. But that aside, it's very, very useful, and it plays a major point in our story. Okay, so a couple mathematical points that I'm going to finish up with, right? And I've already made the first one essentially, and that is one of the reasons that the Helmholtz free energy is more useful than U is that we got rid of S as an independent variable and replaced it with temperature, which is something that we can control in the laboratory. And I did this simply by subtracting TS from U. I'm now sort of talking about math, right? And I noticed that this derivative of TS, which is just this by the product rule, means that when I subtract that from TDS, I get SDT. And this trick is known as a Legendre transformation. It's basically the mathematical term for shifting between two different variables, right? And what I'd like to do is to make sure we understand it. Let's do it again. So F is U minus TS is a function of T, V, and N. And as I just proudly pointed out, the independent variable here is now T and not S, and this helps us a lot. All right. On the other hand, volume, although it's something we can easily measure and in principle control, it's more often, particularly in chemistry, that we'd like to do experiments at constant pressure. So let's say I want to work at fixed pressure rather than fixed volume. Can I shift this variable from V to P? And the answer is yes. I'm going to do it exactly the same way I did it in going from U to F. There I subtracted TS. In this case, because there's a minus sign here, I'm going to add PV. Right? So if I take minus PdV and add the differential of PV, I get VdP. So if I define this new quantity, which I'm going to call the Gibbs free energy, and that's going to be F plus PV, that's U minus TS plus PV. And I can take its differential, right? And we calculated dF before. We're going to add these two things. And now we end up with minus SDT plus VdP plus mu dN. Right? I'm going to be working really with this in the next lecture on Friday. But I'll point out now that the independent variables are T, P, and N. And all three of these things are what we can easily keep fixed in the laboratory. And this is why the Gibbs free energy turns out to be so important in chemistry. And in fact, for many of the examples I had at the beginning of the lecture. All right. So that gets us to our fourth free energy. Like I said, I'll be talking about it more next time. Now, there's another thing you can do mathematically. This is discussed in the text in one of the problems. Right? And that's actually take second derivatives of the energies. So as I mentioned at the beginning, the second derivative of mechanical potential energy is, in the case of the simple harmonic oscillator, its frequency. So sometimes you want to take second derivatives. Right? And for the free energies, the nifty thing is this rule from calculus, the equality of mixed partial derivatives. So df dx, if I take the derivative of df dx with respect to y, that's equal to the derivative of df dy with respect to x. Right? So that's a fact from calculus. My friends in Vincent Hall would make all sorts of caveats, but f is some well-defined function that we're going to assume behaves well. What we're going to do now is let's stick in something like a Helmholtz free energy for this function f, right? And for x and y, I'm going to use t and v. So simply taking this expression and making those substitutions, this is just a statement from math, but df dt, a constant volume, is s, and df dv, a constant temperature, is P. So we've derived this relationship between the derivative of entropy with respect to volume and the derivative of pressure with respect to temperature. Right? And this is one of several such so-called Maxwell relations that can be derived from any of our energies. Right? Now, In a class on thermodynamics, you could spend a long time playing around with stuff like this. I'll just make one observation. The reason we care about Maxwell relations and that they're not just simply exercises in partial derivatives is illustrated exactly by what one I did here. So as we've mentioned many times, entropy is a pain. It's not directly measurable. We can't control it in any way, right? But if in a calculation I came across this partial derivative, I could use the Maxwell relation to replace it with the one on the right, partial p partial t. And these, of course, are things that I can measure and control. So the Maxwell relation provides us with a means to sort of avoid working with a variable that's difficult, like entropy, replace it with working with ones that we do know and love, like P and T. Well, we know and love entropy, we just can't control it. Okay, so let's wrap up here. So just review the main points of the lecture. The first is that the goal of essentially the last part of the semester here is to acquire some of the tools to understand systems that have multiple phases, phase transitions. We'd like to deal with chemical reactions. So this is why we're introducing these new definitions of energy, these free energies. To do so, we would like to use the language of energy. I drew from a couple examples, including classical mechanics, to show why. The problem is that with things like work, PV, heating, TS, chemical potential energy, mu times N, there are a lot of different possible ways to define an energy, and we want to choose only those that are useful, right? And the definition that we choose can depend on a particular set of experimental constraints, such as which variables are being kept constant during an experiment. So I reviewed three of possibilities in detail today. So those are the internal energy U, the enthalpy H, which is U plus PV, and the Helmholtz free energy F, which is U minus TS. We decided that all of these are useful. The Helmholtz free energy has the particular advantage of being minimized in equilibrium at constant temperature and volume and fixed particle number, which is makes it a particularly useful thing. I then defined, I didn't do much with today, the Gibbs free energy. And this will turn out to be the analog of the Helmholtz free energy, in that G is a minimum in equilibrium at constant temperature and pressure, just like F was a minimum at temperature and volume, fixed temperature and volume. So we can see that under everyday laboratory conditions, G is going to be a very useful quantity. Regarding the Legendre transformations of Maxwell relations, I consider these less important, just pointing out that there are a set of sort of standard manipulations that we can do with these energies to calculate other things, either to convert between one form of energy and another, which is what the Legendre transformations do, and to shift around the independent variables, and to derive other things from the free energies, which is what was accomplished in the Maxwell relations. So on Friday, we'll take this up in more detail, particularly the Gibbs free energy. Okay, so we'll finish there.